All right, this is a very brief review of fabrication processes, which I forgot to change this to say lecture 2 apparently. Let's see if I did it on all slides or just this one.
Yeah.
The rest of them are lecture 2?
Yeah.
Good deal. I didn't screw it up that bad then. All right, so what we're going to talk about is the different types of processes that are utilized in the fabrication of MEMS devices. The overwhelming majority of them are also utilized in the fabrication of integrated circuits devices. We're going to talk about patterning processes, material modification processes, additive processes, subtractive processes, mechanical processes, and then kind of encapsulate everything with bulk micromachining and surface micromachining, which are the two most prevalent MEMS processes. So I've developed a little table here. Hopefully you guys can read it. I understand there's a lot of text on there and it's kind of small so that I can fit it all. But effectively we can fit most of the processes that we use in the development and fabrication of MEMS into one of these 5 broad categories: patterning, material modification, additive, subtractive, and mechanical processes. So let's start with a ludicrously simplified review of the photolithography process, which is how we pattern things, okay? So photolithography is a 4, and I'm using 4 loosely here because it's really, classically it's thought of as a 3-step process, not including the cleaning at the end. But each of these individual steps include numerous steps, including priming and soft baking, hard baking, and things like that. So I'm going to dumb it down and say that it is a 4-step process. Photolithography is used to transfer geometrical patterns from a mask onto a wafer. So in a conventional CMOS or MEMS process, photolithography mask is literally a large piece of glass onto which chrome is patterned in a specific pattern. And so if we look here at our first step, this is our deposition step, or this is again overly simplified, okay? The gray layer at the bottom is our substrate, so that is our wafer, and the red layer at the top is our photoresist. So who knows what a photoresist is? Neil, what's a photoresist?
It's a chemical that reacts to light.
Yeah, that is exactly right. It is a chemical that reacts to light. There are literally thousands of different photoresists that are used. The ones that I have the most experience with are 1813, which is a pretty general polymer photoresist, and then SU8, which is an epoxy-based photoresist that makes more permanent microstructures. You literally have to burn or ash off the SU8 to get rid of it, whereas 1813 can be removed just with good old acetone and isopropyl alcohol. So anyway, during the deposition process, you effectively put your wafer on a spin chuck, put a little bit of the photoresist, like pipe it onto the surface of the wafer, spin it at several thousand RPM, depending on the thickness of the resist that you want, and it makes a nice, even, uniform coat, or at least hopefully it does. Prior to that, you might have to put primers like HDMS or HMDS, a primer on it to help the photoresist stick and things like that. Anyway, then when we get to the second step, so this is a mask that has already been pre-patterned. So up here we have the glass section of mask. This is the chrome or chromium parts. And so effectively, when you shine ultraviolet light through this mask onto the surface, the parts that are patterned in chrome block the ultraviolet light from going through. So you don't get any light touching your photoresist here. In this place, we have a gap in the chrome, and so the light passes all the way through, and a chemical reaction is going to occur. That chemical reaction tends to harden the photoresist. So that's a chemical process called cross-linking, effectively. You turn your liquid into a plastic or polymer in very specific regions, and then it stays roughly liquid or cross-linked anywhere that the ultraviolet light was blocked. Our third step, and I'm neglecting bakings and things like that, is development. So when I was doing all of this kind of stuff in graduate school, the development was carried out in a bath. You literally submerged your entire wafer in a bath. Specific developers are used for specific types of photoresist. And in this case, we have this would be a positive photoresist. So effectively, wherever we had a hole, we're removing the cured photoresist. There are also negative photoresists that work in the exact opposite way. Everywhere the light shined through would stay, everywhere the light didn't shine through would get removed during the development process. Modern development processes actually, instead of soaking your whole wafer in a bath, they use a depositor much like you deposit your photoresist. You just deposit some developer on the surface and remove the material selectively. And then the last part of the photolithography process is cleaning, where you're removing all of the chemical solvents and all that kind of stuff that you don't want anymore, leaving a patterned photoresist layer atop your substrate. Give me just a moment because my wife is calling. Be right back. Sorry. Yeah. Sorry about that. My dog is at the vet and I wanted to tell my wife what was going on before I forgot what the vet told me. So, all right. So this is a very simplified view of the photolithography process. Photolithography gets carried out tens, if not hundreds of times, depending on the complexity of the structures and things like that that you're trying to make. So this is really going to be a part of several of the other steps that we are going to see. So now we're going to look at material modification. So this is how do we change the behavior of the substrate material largely. So in this example here, we're going to talk about ion implantation, where we have a photoresist mask generated by the photolithography step, which is going to effectively work to block ions from being able to penetrate the surface of the substrate in specific areas. So we have a physical mask that is going to prevent ion implantation. In an ion implantation process, this is typically carried out at room temperature for the implantation part, and the surface of the wafer is bombarded with ions, okay? The type of ion will have a different size and a different associated energy, and that will tell us effectively how far the ion will get implanted into the surface of the wafer. So one thing that we have to do in an ion implantation process is make sure that our physical photoresist mask is thick enough so that the ions don't pass all the way through it and get implanted in the surface underneath the resist, okay? So we have to make sure that we have a fairly thick layer of photoresist. Then we effectively shine this beam of ions on the surface of the wafer. Typically, it's much more collimated than this because there are electromagnetic lenses and things like that that are in play to focus the beam in specific areas. We effectively shoot a bunch of ions at the surface of the wafer, and then we turn the beam off and we do an annealing process. So effectively, during the irradiation process, we're going to have an extraordinarily thin layer of ions at the surface here that have been implanted, and they're going to have some mean depth dependent on their energy and all of that kind of stuff. The implantation process tends to actually deform the surface of the wafer and cause damage. Imagine if you were hitting golf balls at that brick wall as fast as you possibly could. Over time, it's going to make little chips and divots and things like that on the surface of the wafer. So the annealing process, which is carried out at a very, very high temperature, what it does is it effectively removes all of that mechanical stress from that interface, and it helps to drive the implanted atoms deeper into the wafer surface, yielding a concentration profile, something like this, where we have a region where we have a fixed concentration of dopant atoms. Typically speaking, for ion implantation, we get a relatively large dopant concentration or relatively high dopant concentration, as we'll see from other processes. Okay, so we have a very low temperature step under the irradiation. I say low temperature, room temperature step, and then we have a very high temperature annealing process. In contrast, this is diffusion. This is what was used to be done until the late 1980s. Now practically everything has moved over to ion implantation. So for a diffusion process, instead of using a photoresist mask, we typically use an oxide layer mask. So we have to thermally grow an oxide. We'll talk about that a little bit later. That is patterned through some sort of chemical etching. And then we expose the entire wafer surface to a gaseous cloud of dopant atoms. And then we use electric fields to effectively drive that cloud towards the wafer surface. Some of the dopant atoms get driven into the oxide, which we're going to strip away later anyway, so that doesn't particularly matter. Other dopant atoms are going to get drawn into the substrate itself because there is a concentration gradient, right? So that's what diffusion is all about. If there's a high concentration of impurity atoms here and a low concentration of impurity atoms here, because we're using electronics grade silicon, effectively we'll see that the high concentration wants to move into the region of low concentration. And we do this at a very, very high temperature, close to 1,000 degrees Celsius, in order to give the wafer enough energy to have these atoms move inside. The drive-in process is effectively a similar thing to what we saw with the thermally annealing process for the ion implantation. We turn the source of the gaseous dopant atoms off. We ramp up the temperature, and effectively what we're going to see is diffusion. So atoms are moving from an area of high concentration into an area of low concentration. We see lateral diffusion a lot in the diffusion implantation process. So instead of just driving our dopants down, we drive them down and out. So we have a swelled region of dopants. All of the exposed regions have effectively the exact same dopant concentration because the entire surface of the wafer is doped at the same time. So it's exposed to effectively one specific dosage, and how much you get depends on how long you leave the wafer in that environment and all that kind of stuff. So you can't have a different concentration here versus a different concentration there. Everything is at the exact same level, which for some devices can be problematic. All right, and then now let's talk briefly about thermal annealing. Effectively, we use an extremely high temperature to bake our wafer in. We do it in typically a nitrogen or a nitrogen and hydrogen environment. No oxygen, because the purpose of this is not to grow oxide layers, it is to relieve mechanical stresses and things like that. It can also densify thin films, so effectively it can drive solvents out. The high temperature can cause evaporation of solvents, which makes the thin films that you've deposited using another process more tightly bonded and all that kind of good stuff. All right, now we're going to talk about additive processes. So first we're going to talk about thin film depositions, and specifically physical vapor deposition, or PVD processes, which will be contrasted with chemical vapor deposition, or CVD things on the next slide. So physical vapor deposition is either done using evaporation or sputtering, two similar but different technologies, okay? So evaporation is exactly what it sounds like. You literally heat the material that you're trying to deposit onto your wafer surface up so hot that it goes from a solid or liquid state into a gaseous state, and then it literally condensates on your substrate, leaving behind layers of the material. You can do that through resistive heating, which is shown over here on the left, or e-beam heating, where you're effectively causing friction by firing electrons at your target so much that it causes it to heat up and evaporate, okay? Sputtering is effectively you're shooting ions at your target, knocking off chunks of material, and then you're trying to draw those knocked off chunks of material to your substrate to form a moderately uniform layer. So it's called sputtering because the bits of material sputter and fits and starts and clump up on the top of your surface. It works a little faster than evaporation. Most of my experience with sputtering was never to actually make a thin film for a purpose. It was for characterization. So to use certain metrology tools like SEMs and FEMs, you want to make sure that your surface is conductive. So you would sputter gold over the whole thing so that you could look at it with a scanning electron microscope. Anytime I wanted to actually use a layer for a purpose of the device, I used evaporation, just because you get nicer and neater, in my opinion, layers. All right, chemical vapor deposition. So very similar to physical vapor deposition, the purpose here is to grow a thin film, but instead of condensing, you flow a source gas in, it reacts with your substrate. So some amount of material gets deposited on your substrate, and then also volatile compounds get created. And then you use a vacuum system to draw those volatile compounds off, leaving behind effectively a nice thin even layer of thin film on top of your substrate. Thermal oxidation is effectively annealing, but in an oxygen-rich environment, so that you intentionally grow an oxide layer. That one's pretty straightforward. Now we have our subtractive processes. So there are three that we're going to talk about: plasma etching, reactive ion etching, and wet chemical etching. Wet chemical etching is the original thing. Plasma is what was done in the late 90s. Reactive ion etching is what's done more recently. So plasma etching means you literally excite a gas into its plasma state. This gas chemically reacts with the material on the surface of your wafer and eats away at it, and then you pump out all of those volatile compounds that occur during the reaction. So you're just removing material kind of slowly, but you get a pretty anisotropic etch profile. So anisotropy versus isotropy, directional versus in all directions at once, okay? So plasma etching gets you reasonably vertical sidewalls, not too much undercutting, which is what I'm trying to show you on the right-hand slide there. Reactive ion etching is effectively very similar to plasma etching, except that it's more dependent on chemical reactions as well, and you get nearly perfect vertical sidewalls. I'll have to find my slides that I made for the work that I was doing for an Air Force research project and show you guys what I was doing with deep reactive ion etching, but I was getting, trenches that were several tens of microns deep with less than a micron of, what would you call it, slope or whatever on the sidewall. And then finally down here, we have wet chemical etching, which is still used in some cases. You expose your surface to a chemical bath. Because it's purely chemical reaction based, it happens in all directions equally. And so you wind up undercutting your mask layer and all that kind of stuff, which can cause the mask layers to peel off, generally bad, and ruin things. So still useful, but you have to be rather careful about it. And then let's see, we have our last couple of things here, the mechanical processes. So polishing, this is literally just making the surface of your wafer a flat plane, getting rid of all of any kind of indentations and ridges and all of that kind of good stuff. Wafer bonding is used in a lot of bulk microfabrication processes. It can also be used to grind down or lap your wafers and all that kind of good stuff. I didn't realize this image was going to look so shitty here, or I would have chosen a better one. But effectively, wafer bonding is exactly what the name implies. You bond two different wafers together using either adhesives or heat to fuse them together. Here we have wafer dicing. So all of the processes that we're talking about are batch fabrication processes. So you can do it to hundreds, if not thousands of devices at the same time. Then you have to break your wafer down into individual devices. That's what the dicing process is all about. There are a couple of different ways to do it. The old school way is literally with a saw, a specific dicing saw that slides across and cuts the wafer up into square or rectangular regions. A more modern method, which is what's shown here, is instead of using a saw, you use a scribe. So it's a diamond tip that slides along the surface and makes a very, very thin scratch in the direction of one of the crystal planes, which allows the wafer to be physically broken very easily along those lines without any particular losses or anything like that. The most modern wafer dicing method that I've read about is, I think they called it stealth dicing, where effectively you use not fully transparent light to somehow etch the wafer from the inside out in specific patterns. Read about it for about 2 minutes, so not super sure on all the physics and all that kind of stuff behind it. The reason why the stealth dicing though is coming in the forefront is because there's no mechanical deformation. You don't have little shards, or it doesn't create any dust or anything like that. It is purely etching based, so all of the bits and pieces get pulled off and you don't have any risk of contamination of your surfaces. Next we have wire bonding. So wire bonding is bonding wires between bonding pads on your chip and in the packaging. It's the only way you can get signals on and off your chip. So effectively I'm going to call it solder, but that's not the right word. Solder extraordinarily thin wires, smaller than a human hair, between 2 points. So this is done with mechanically. This is done using tools and all this kind of stuff. This is the physical implementation. So this is where you as a person can interact with the chip, because you can't interact with these bits here reliably. Then we have packaging, which is effectively just encapsulating your device in a package for external use. So this is a simple dip dual inline packaging, like we're probably largely familiar with. And then on the right-hand side, we have a kind of evolutionary chart of how packaging has progressed over the years to different types of pins and all of that kind of stuff. The bulk of it is you put your chip on a platform, encapsulate it in some sort of plastic or epoxy that has leads sticking out so that other people can actually access the functionality of your chip. All right, so these are all of the different types of processes that go into the creation of a chip. Very, very loosely, I'm actually considering crowdsourcing you guys into helping me make this lecture better by making a homework assignment. 3 to 5 slides of talking more in depth about one of these things, and then I will give you credit. And next year, this lecture will be less shitty. So we'll see. All right, bulk micro machining. We have our 2 last slides here. So bulk micro machining is effectively how do you make large structures, okay? So bulk micro machining involves processing the substrate itself, making very physically large structures. So on the right-hand side here, this is effectively a skipping tons of steps way that you would make a bulk micro machine accelerometer, right? So you start off with something like a silicon, the SOI, silicon on insulator wafer. You do patterning and etching to remove some portions of the wafer, both on the top side and on the back side. You do further etching and processing to effectively release your proof mass from the bulk of the bottom substrate. Further etching puts effectively these mechanical springs here and here. These little sections of silicon are nothing more than a spring. You would very likely also do either an ion implantation or a diffusion process to integrate piezo resistors or some type of sensing mechanism into this as well, so that you have a way to measure how much the proof mass moves, either by beam deflection or something like that, into this as well. And then we have a wafer bonding step where you encapsulate the top and the bottom, so that hopefully this is done in either a vacuum or at least some sort of fixed pressure, so that you know how much air damping is going to happen, so that you can translate that into a measurable electrical signal or known quantity. Okay. So this is the bulk micro machining process in a very simplified view. Done a whole heck of a lot up until the mid 1990s, still done now for specific things like pressure sensors and stuff like that. In contrast, we have surface micro machining. So instead of manipulating the substrate, you build structures on top of the substrate using patterning and sacrificial layers. So here we have another simple accelerometer, this one based on a cantilever beam, right? So you deposit some sort of sacrificial layer, pattern it. So here we're just simply cutting a hole out of this sacrificial layer in order to deposit a thin film on top. We pattern the thin film to get our cantilever structure, and then we remove the sacrificial layer, releasing the cantilever structure so that it can then deflect. And then we would have some sort of integrated circuitry to measure that deflection. One of the biggest benefits of surface micro machining is that it's largely done with purely planar things, so that it is, for the most part, completely and utterly compatible with MOSFET IC processes, so that you can monolithically integrate your MEMS device and your measurement circuitry on the exact same chip during the same process run, so that everything is integrated and you don't have to worry about bonding things and this, that, and the other. All right, so that's what I wanted to talk about for today. On Monday, we are going to review electrical and mechanical properties, talk about shear, stress, strain, all that kind of good stuff, crystal planes, and then finally start doing math and things like that. So